Welcome back, folks. This is going to be a continuation of kind of soil organization, but right now we're going to talk about how soil itself formed, and then we'll go into kind of how we organize it and classify it. So, soil formation from parent material. I want you to really understand the physical and biogeochemical processes that rocks and minerals undergo weathering. I want you to list the 5 soil forming factors and quote the related definition of soils. We're going to describe the relationships between residual, transported, and organic parent materials. We're going to talk about some influence on temperature and effective rainfall on soil formation, basically how climate plays a role. We're going to talk about how biology plays a role in soil formation via the influence of plants and animals. And I want you to really kind of be able to demonstrate your understanding of all of these different formations and how soils differ in soil formation. I want you to be able to write a brief description of how and why each soil could differ in soil formation based on its climate, the biota that lives there, and a variety of other influences. We're going to talk about topography and how it influences soil properties. We're going to talk about the basic processes of soil formation and how different areas of the world have different soils because of this. So, normally I would have you do a course chant, but since we're not necessarily all in the same room together, just chant this with me from your dorm room or from wherever it is that you're watching this. And if you're at Starbucks, be prepared for some funny faces. Soils have different origins, which give rise to different properties, which require different management, right? So, we're going to talk about minerals that give rise to some of these different properties. First, we're going to talk about primary minerals, which are formed as molten lava solidifies. It is not chemically altered. We also have secondary minerals, which are recrystallized products of chemical breakdown, and these are basically primary minerals that get weathered into something else. So they're altered primary minerals. They've been altered chemically. All right, so back to primary minerals. Some examples of primary minerals that you're going to see in lab are quartz. We generally see this in sands. They weather very, very slowly, so they end up staying in the larger fraction of soils, which are sands. Feldspars weather very slowly to soil clays. Muscovite mica are thin translucent sheets, say that 10 times fast, that weather into soil clays as well. Now, this is the kind of fun part of the class where you get to play with all of these little minerals and see them. And I mean, who doesn't love collecting rocks? Let's be honest, as a kid, you all had rock collections. All right, primary minerals. Biotite, you'll probably see this in a lot of either fake or real granite countertops. This is usually what that little black speck is. You'll also see hornblende, which is more of a brown color, more of a brown speck that you'll see in countertops. Olivine is a beautiful deep olive green. Must be why they call it olivine. Some of the secondary minerals. Aluminum and iron oxides and hydroxides, sometimes called sesquioxides, but this isn't a mineralogy class. We're not going to go super deep into that. Goethite, a source of iron. Gibbsite, an aluminum hydroxide. Very stable soils have these minerals. They're very old. This is the end of the weathering sequence. Aluminosilicate clays are very common in soils. The salts that we see, calcite or calcium carbonate, dolomite, calcium magnesium carbonate. This is very common in this area, actually. We see a lot of dolomite here. Gypsum, which contains sulfur, which is important. So, one of the things I want you to look at is I'm never going to ask you to memorize any of these names or equations. But if I were to give you this formula and I were to ask what individual nutrients does this mineral release to soils, you would say, oh, goethite gives me iron. Calcite gives me calcium. Dolomite can give me magnesium. Gypsum can give me calcium as well as sulfur. So things like that are where we're going with this kind of information. Rocks themselves are mixtures of minerals, so they're heterogeneous. If you've ever really looked at a rock, you can see that it's a bunch of different colors. So it's a heterogeneous mix of all these different minerals. The texture itself is the size of the minerals. If they're fine, they're very, very, very tiny, and you have to use a magnifying glass to see them. If it's intermediate, you might be able to see it without a magnifying glass, depending on your visual capacity. The coarse textures, though, those are the ones that are really easy to visualize, and I'll give you some examples. Minerals and their individual texture sizes determine weathering rates of soils. And we'll talk more about this. So there's three basic types of rocks, and we're not going to focus on this in great detail, but this is important to understand for the formation of soil. So we have igneous rocks that form as magma cools underground. This is an intrusive, or at the surface, an extrusive process. Okay, and that magma cools down and solidifies into a rock. Okay, and then over time, that rock is weathered through erosive properties, processes, and it breaks them into smaller pieces called sediments. Okay, and those sediments are transported and then eventually they settle somewhere and they're glued together again. Okay, and that forms a sedimentary rock. And then that rock undergoes high temperature and pressure when it goes back down into the earth, and it changes either the igneous or the sedimentary rock into a new rock. Okay, and we call these rocks, the ones that undergo high temperature and pressure, much like you may feel at exam time, we call these metamorphic rocks. Metamorphic rocks often show layered or foliates of texture due to the growth of crystals under the pressure. Okay, they melt back down and go back into magma, and the process continues. Igneous rocks. Okay, here's a great example of coarse texture in the upper right, where you can see the grains of individual minerals very well. Uh, Igneous rocks, again, these are rocks cooled from molten magma. They have primary minerals. In granite, we see coarse textures of, of quartz, feldspars, some darker minerals like biotite or hornblende. These are very slow to weather, okay? Takes a long time to break these down. Basalt has a fine texture, which means it's really hard to see the individual minerals without the aid of magnification. Normally, this is made of hornblende and other darker minerals. And because of its fine texture, aka small particle size, it weathers very rapidly. Just to note, in general, the darker the color of the igneous rock, the faster it's going to weather, is something that I've found. All right, sedimentary and metamorphic rocks. Sedimentary rocks are created through the deposition and re-cementation of weathering products from other rocks. So this creates things like sandstone, shale, and limestone. Metamorphic are where we take igneous or sedimentary rocks that are transformed by high heat and pressure, and we morph them into something else. So a granite rock example gets morphed into something very nice. See what I did there? Oh, schist. I know, my jokes, they're terrible, but nice and schist. Oh, schist. All right. Shale gets transformed into slate. Sandstone gets transformed into quartzite. Limestone gets transformed into marble, which is like all the rage now on the home fixer upper shows. P.S. Did you hear that the games are creating uh another season of Fixer Upper? My heart is so happy. All right, so I want you to note that the majority of rocks, about 75% of rocks on the Earth's surface, are sedimentary. So here we see sandstone. This is an example of sandstone on the left. And there's an example of fossiliferous limestone on the right, meaning limestone that's full of fossils. Pretty fun, huh? Look at all those cute little boogers in there. On the left, we have gneiss, which is metamorphized granite. Was igneous when it was granite, and then it gets metamorphized and turned into gneiss, which is the metamorphic rock version. On the right, we have my very favorite rock. I know it's silly, but I love slate. I want like all the floors of my house slate. I love it so much. Weathering. This happens at or near the Earth's surface by atmospheric agents generally, and there's two categories of weathering. There's both physical and chemical. Brady and Wheel have a great figure that kind of breaks down how minerals disintegrate very slowly, or easily, and what they kind of turn into, and how they change in different ways, and what different minerals change in those ways, and what they ultimately turn into. Physical weathering is disintegration. It is literally when something physically gets smaller. It's accentuated in very hot or very dry environments. The temperature definitely has an effect. We either have an exfoliation, we have oh goodness, freeze thaw action. So water comes in, cracks in rock, for example, and then it freezes and it expands, and then that rock breaks up a little bit more, and then it melts again as it thaws out, and then more water comes in, and you see where we're going this over time. This breaks rock down. Water, wind, and ice certainly have a huge effect, and we see a lot of that effect here in Indiana, where the glaciers came through and completely transformed the entire landscape. It's been pretty incredible, the transformation that we see here. So, other transformative features of water include rain, runoff, wind erosion also has a huge effect on transformations and physical weathering. Organisms like roots and soil animals and mankind have a effective change on physical weathering. You'll see where there's a divot in a rock, and over time, tiny trees will grow there, and the acids that their roots exude slowly break down that rock into larger and larger portions of soils. And other types of plants do the same thing. Chemical weathering, which is really biogeochemical weathering, alters the actual composition of rocks and minerals. It's a conversion of primary minerals into secondary minerals. It's definitely rapid in hotter temperatures where there's more water and particle size is smaller. All of those variables will essentially make any reaction go faster. Chemical and physical weathering act together. It's not just one or the other, it's usually both happening at the same time. Chemical weathering includes biochemical impacts as well. Water is very important to this process, and there's various chemical processes involved, known as hydrolysis, hydration, dissolution, oxidation, reduction, and complexation. I'm going to go briefly through these chemical processes, but I don't really spend a lot of time on them because I would go into these in greater depth in more upper division classes. So, hydrolysis, one of the chemical weathering processes, is where we add water across a bond. This is an important mechanism for releasing nutrients from minerals. Here's an example of what that may look like as a chemical equation. Again, I don't expect you to know this chemical equation. It's just an example for those of you who are more visual. Here, we get potassium as a result of adding water across the bond. Hydration is where we add water to a chemical structure. So in this instance, we have the example of hematite, which is an iron mineral, obtaining water into its chemical structure, and then it is transformed into a mineral known as ferrihydrite. Chemical weathering processes also include where we add carbonate and other acid reactions. So in root and microbial exudates, atmospheric deposition essentially melts, or in other cases brings things together. But in this case, it's really melting something down. And so we see this in older limestone based graveyard structures. If you notice, they start to become rounded and watered down because they're slowly disintegrating from basically acid brought in from rain, where it forms carbonic acid and slowly breaks it down. And we also see this as creating essentially sinkholes underground, but we'll go into that more later. mediated by soil biological processes, the process called complexation. And so the example given here is where muscovite and oxalic acid undergo complexation to create potassium hydroxide and an oxalic acid aluminum complex, leaving silicic acid in solution. So essentially, some organic acid comes in and breaks down the mineral to dissipate it, and we lose some of the silica into solution over time. Chemical weathering processes include dissolution, where many minerals dissolve in water. Gypsum is an example of one of those. And so when you put it in water, it dissolves into its individual parts and releases calcium and sulfur compounds into the water, which is great for plants, by the way, because they love these things. Oxidation and reduction is the loss and gain of electrons. So you may have heard of LEOGR to help you remember this. In one direction, we have oxidation occurring, and in the other direction, we have reduction occurring. And so we see this in the example of iron plus 2 on this side versus iron plus 3 on this side. So LEO stands for the loss of an electron is oxidation, where the gain of an electron is reduction. Electrons are negatively charged. So if we gain an electron, then we're undergoing reduction and coming down to 2 plus from 3 plus, right? So if we gain an electron, we're knocking 3 down to 2. Whereas if we lose an electron, this is going to become more positive. And so we undergo oxidation to move to a 3 plus. And so that's just kind of a little brief introduction into oxidation and reduction, which becomes important in wetland and soils where we have a fluctuating water table. We'll see some beautiful examples of soils that have undergone oxidation and reduction later on in class. In summary, weathering undergoes two overall processes. It's either physical weathering, which is the disintegration processes which increase surface areas of rock minerals, or chemical weathering, which are processes that result in the conversion of minerals into other minerals. We go from a primary to a secondary mineral. And these are the processes that release nutrients from soils, which is a good thing. I'm going to skip through this. This isn't something that I really care about, to be honest. All right. So here's a brief review for you to kind of think in your head at home, maybe what some of the things that we've gone over. So name 2 mineral types and the difference between them. Name 3 types of rocks and the difference between them. And name the 2 primary types of weathering. And how do they alter mineral and rock in weathering processes? What are hydrolysis, hydration, acid reactions, complexation, dissolution, and oxidation reduction? Be able to identify them, but don't spend too much time on that. Is it a low or high silica to aluminum that indicates a more weathered soil, and why? And what are 5 soil forming factors? Now, these last 2 questions, you're probably thinking, I don't know, we haven't gone over that. That is correct. Let us do that then. Is the function of climate, biota, parent materials, topography, and time. And what I do for this, let's see if I can write with this, don't laugh, is I remember it with this silly mnemonic. This is supposed to be an O. Y'all, this is going great. I hope you're laughing at home because this is marvelous. Chlor. Oh, goodness. Chlorpt. I need a whiteboard, folks. This is rough. Okay. Cl is for climate. Oh, come on. This O is supposed to be for organisms or biota. R is for relief, also known as topography. P is for parent materials. And T is for time. Okay, so this just helps me remember it. Chlorpt. This is supposed to be an O Don't mind me. I just suck at drawing with. There we go. Nope, it's just not going to happen, folks. It's just a beautiful musical note. We're leaving it at that. Plorped. Climate, organisms, relief, parent material, topography. If that helps you use. All right. Parent materials is the first factor in soil development. All right, so this is going to determine the texture, the fertility, and the types of clay minerals seen in soils. There's 3 classes of parent materials based on placement, and then the third one has 6 subclassifications. So the first is residual parent material, the second is organic parent material, and the third is transported parent material. Okay, so we're going to talk about each one of these in following slides. So we've got the residual parent material, we have organic parent material, and then we have transported parent material. And when we get to the transported parent material, we're going to talk about 6 subclassifications, and all of these are very important for you to know and understand. Residual parent material is formed in place. Okay, so it's literally just rock that weathers right where it's at and turns into soil. So limestone, weathering in place, tends to give us really clay soils. Sandstone tends to give us really coarse acidic soils. Granite tends to give us very coarse acidic soils. Slate and shale both weather in place to give us clayey soils. And so here is where parent material that is residual comes into importance, is the type of soil that it weathers into. Okay, so again, residual parent material is formed in place. Organic material is formed in places where it's very wet and the plant growth exceeds the rate of decomposition. So basically, plants are growing faster than they're dying out and then decomposing. And so you get this giant collection of plant smush that we usually call peat. About 75% of peatlands in the world are found in Canada and northern Russia, and they're absolutely endangered. You can learn a lot more about organic parent materials by taking the wetlands class, which is NREM 320 and is offered fall of 2021, and then every 2 years after that. Let's talk about the 6 types of transported parent material, okay? So this is the third type of parent material. The first was residual, the second was organic, and the third being transported. Now there's 6 different types of transported. First is colluvial. Colluvial parent material is any parent material that's moved by gravity, okay? And we're going to go through some examples of this. Alluvial parent material is deposited by streams and rivers. Okay, so it's transported by streams or rivers, and we call that alluvial. Marine parent material was deposited in oceans. Lacustrine parent material was deposited in lakes. So you're noticing now that we're breaking up the different types of transported by the type of water that moved it. Okay, so alluvial was streams and rivers, marine was oceans, lacustrine was lakes. We also have transport by wind, known as aeolian. So aeolian transport is where soil is deposited by wind. Okay, so it's a soil parent material that's transported by wind. Glacial parent material was deposited by ice. So most of Indiana has glacial parent material that was deposited by the glaciers that came through. So let's talk about these 6 individual transported types individually, okay? Colluvial materials. These are the ones that were moved by gravity, okay? Essentially, they were moved by some kind of rock or mudslide. So they're going to have poorly sorted fragments at the foot of a slope. So you can tell that it's just like a jumbled up mass of things moved as they tumbled down a hill, basically. We generally see these in small geographical areas. Usually they're rocky and stony due to greater amounts of physical rather than chemical weathering because of the actual movement of gravity. We see chemical weathering not very much. Instead, we see more physical weathering. All right, alluvial deposits are basically water deposits by streams and rivers. So we're going to see most of these in floodplains, where we see a lot of sediment deposition, and the sediments that are deposited are like stratified in weird ways. Okay, we see horizontal and vertical stratifications. Now, if you learn nothing from this class, I want you to learn to never, ever, 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 ever choose a home in a floodplain. Everybody wants to do this. Everybody wants to live right next to a river. Now, if you build your home right next to a river, you are in a floodplain. Guess what floodplains do? I know this is going to shock you. It's going to blow your mind. They flood people. Floodplains flood. Don't build your home somewhere where it's going to flood. Eventually, you're going to have water in your home. Even if it's a floodplain that barely ever floods, okay? Unfortunately, in California, there are people living in riverbeds. They have literally built housing developments inside an actual riverbed because it has rained so little in the last 50 years. They've started developing closer and closer and even inside riverbeds. And guess what happens whenever we get one of our crazy 5-year flood storms that are only supposed to happen every 100 years, but they somehow happen every 5? They flood, and then they're all surprised that their homes are filled with water and horrified. And it's like, well, you built in a floodplain, you nimrods. Anyways, I go on tangents about this all the time. This won't be the first time. This won't be the last. Don't build in a floodplain. All right. Terraces are old floodplains that have been lifted up. Okay. These are a little bit more safer to build in, depending on how uplifted they are. They're usually very, very, very fertile ground as well. Alluvial fans, alluvial deposits. We usually see these in delta deposits, okay? Essentially, they can come out of the drainage way from mountainous regions. In that case, we see them being very gravelly and stony. Or in delta deposits, we usually see them at the base of a river as it floods into uh, another larger body of water, but generally at this point it's a very slow deposition, and so we see much smaller fragments like clay and fine silt being deposited in delta deposits. So these are all alluvial, moved by streams and rivers still. Let's move into marine and lacustrine sediments. Marine sediments, also called coastal plain sediments, are ocean sediments that are built up over time. Okay? Generally, these materials are gravelly, sandy, clay, depending on the area, basically. The Atlantic and Gulf coastal areas make up about 10% of the United States. Okay, so the coastal plain includes the fall line, which is basically the shore moving all the way out to the ocean beach, okay, which is where everybody likes to hang out. So the fall line is where we get basically, we move off of higher regions into the flat area, aka the floodplain of the ocean. But we call this, instead of a floodplain, we call this area the coastal plain, all the way from the shore to where we see the upland area. This is all a coastal plain, all right? So instead of a floodplain, we're calling this a coastal plain. So this includes an estuary, which are those small areas that become like marshlands where the storks and the egrets hang out. And if you've never been to like the Louisiana coast and seen some of the most amazing swamplands and marshlands, oh, you must go. They're beautiful. All right, I'm going on a tangent. Lacustrine. These are clayey soils formed in old lake beds. So lacustrine is formed by lakes. And here you can see a dried out lake where you can see years and years and years of lake shore deposition. Each one of these lines represents another wave area that was deposited over the course of several years. And so if you've ever gone to the lake, you see that it's generally murky. All that murkiness is basically clay and silt floating in the water. And over time, usually over winter when there's not as much turbulence in the water, those settle and they create these lake bed lacustrine deposits. They're really cool to see. There's some really amazing glacial lacustrine deposits. And if you want to learn more about that, you should take the NREM 324 class, which is called Soil Classification. And that's offered in the spring this year and then every other year after that. So Lake Cumberland's Burnside Marina is a great great example of lacustrine deposits, which are clays formed from an old lake bed. Aeolian deposits. Now, these are wind-blown deposits. A great example in this area is called loess, all right? We don't have a lot of loess here, but as you go south, you get deeper and deeper loess deposits. It's basically just wind-blown silt. Okay, so as the glaciers came through, they decimated the landscape and they exposed all of the soil, and these smaller particles, especially silts, they are most prone to being moved by wind. And so they were carried off and deposited all over the South. And so that's why south of us has much deeper loess caps. Here you can see a nice deep, thick surface horizon of loess, this dark brown surface cap versus this lighter surface cap here. I can't draw on this thing. Um, I'll just draw a flower up here. That makes it better, right? If I can, whatever. The daisy. That's supposed to be a daisy. All right, we're just gonna roll with it. I can't draw. It is what it is. Now it looks like the Eye of Solomon. I don't even know. All right, moving on. Moving on. They basically cover up other soil parent materials. And so that means you can have more than one parent material. Okay, and so we'll get into what that means when we get into soil classification, but especially loess is a great example of this where you basically have a cap of something drawn at the surface. Okay, this cap is the loess aeolian deposit, and underneath it, there could have been residual deposits, or there could have been colluvium from a mudslide before, something like that. All right. Other examples of aeolian deposits are sand dunes, volcanic ash, or aerosolic dust. Sand dunes are just windblown sand at the shoreline. Glacial deposits. All right. Glaciations have occurred several times in the last 1.5 million years. We have the Kansas, the Illinois, and the Wisconsin glaciation. There's two major types of deposits. There's glacial till and there's glacial outwash. Here you can see a map that shows the area of the United States covered by the continental ice sheets. And it came down to this line right here. Okay, that's how far it glaciated. And then essentially all this dark area, sorry, I should have drawn it basically like this. Okay, and all this dark area is all loess that was blown off of these glaciated regions. And if you see this finger that comes down to the Gulf of Mexico, I want you to think, what body of water could have carried these loess deposits down in this finger-like formation towards the Gulf of Mexico? And if you're thinking the Mississippi River, ding, ding, ding. All right. These are just all of the major parent materials that are residual shown across the United States in terms of a physiographic province, all the different provinces. So you can kind of see how the Appalachian Mountain Range has its own province. The coastal areas have their own provinces. There's various belts based on, the Great Plains, for example, etc. And what are the different various major parent materials involved there? I'm never going to ask you these questions, just kind of a cool thing to see and know and understand. Let's focus on Indiana, all right? Northern Indiana has Wisconsin-aged glacial deposits, whereas southern Indiana has pre-Wisconsin-aged glacial deposits that include sandstones, shales, limestone, and very deep loess. And what's cool about southern Indiana is if you've ever driven from northern Indiana all the way to the tip of southern Indiana, you've probably noticed that up here in the northern area, it's very, very flat. Right? It's very flat as you go through this area. And then all of a sudden, once you hit this line, it starts getting very hilly. And I don't know why I'm saying that as I draw, but whatever. So as it goes down through southern Indiana, you get a lot more topographical differences, all right? And so we actually start getting much thinner glaciated parent materials, and you can actually get down to see where we have our residual parent materials. So it's very cool in southern Indiana to see the soils there. All right, so all of that was just parent materials influence on soil formation. Now we're going to talk about climate's influence on soil formation. Now, climate affects formation in two ways. It can either be effective precipitation or temperature. For effective precipitation, we're going to say that as rainfall increases, chemical and physical weathering increases and can influence the depth of profile, because the more water, the more ability to move things via water through the profile, which increases the number of horizons developed because we see more illuviation and illuviation happening. We see nutrient loss through leaching processes of water moving through the profile. And because of this, we see acidity increasing. Effective precipitation is going to depend on seasonal distribution. Is it effectively distributed across all 12 months, or is it concentrated in one or two seasons? What are the temperatures like during those times versus evaporation rates, right? Because temperature drastically affects rainfall's evaporation back into the atmosphere, or the ability of that rain to move through soil. Topography, or the shape of the land, is going to influence effective precipitation as well. The steeper the slope, the more likely, depending on vegetation and soil permeability, the more likely water is going to run off of the soil instead of going into it. Permeability basically means the ability of soil to take water into it. How easy is it for water to move into the soil? Is the soil soft and supple and have a lot of pores to take water in, or is the soil hard and compacted and water can't move into it very easily? All of these things are going to have an effect on how well precipitation is going to move in and through the soil and what changes it can make there. Temperature affects the rates of chemical and biological processes. Rates more than double for every 10-degree Celsius increase. And this takes us into physical weathering as well, which of course is going to be affected by temperature as well. Factor 3, biota, organisms, plants, animals, micro and macroorganisms. These are very important for many processes in soil formation because they affect chemical weathering. Lichens, for example, growing on a rock, exude acids that break it down over time. Organic matter accumulation, the acids from that can break things down over time, but also organic matter feeds the various biota in the soil. So the more organic matter you have, the more different organisms you have living in the soil. And that makes a big change. Organisms that live in the soil mix the soil, which changes the various horizons. And this is a good thing. It also allows aeration of the soil, which is hugely necessary for biota to survive there. Aggregate stability is something that we're going to talk about when we get into the physical properties of soils. Now, aggregate stability is important because basically soil breaks up into different shapes. And those shapes can break apart easily if they don't have good aggregate stability. And what increases aggregate stability are natural glues, which are derived from organic matter. So what we're going to learn about later on is that the more organic matter you have, the more glue you have to hold soil particles together and make stronger structure, which develops better pore formation, which allows water and nutrients and animals to move in and out of the soil in better formation. And it all comes down to organic matter and aggregate stability, people. We'll learn more about that later. I'm going on a tangent. Biota are involved in nutrient cycling. They recycle bases, they recycle calcium, magnesium, potassium. They're responsible for additions of nitrogen to the soil. In certain microorganisms can actually take nitrogen from the atmosphere and change it into plant available nitrogen, which is a part of the nitrogen cycle for the health and well-being of the planet and the pedosphere and atmosphere continuum. Profile mixing is called bioturbation, and this is done by earthworms, insects, other organisms that live and move throughout the soil. Different types of vegetation will also influence soil formation. In humid regions, forests are going to have drastically different soil formation than in the subhuman, semi-arid prairie and grassland soils. In an arid desert environment, we're going to see shrubs, brush, and succulents. And they're going to have much different soil formation because of the difference in root systems and the difference in translocation of nutrients and the difference in rainfall and lots of different things that come along with these different vegetation types. So here we're going to compare some different vegetation soils. All right, so in a grassland soil, we call these mollisols. There's 12 soil orders that we're going to go over eventually, but for now, we'll focus on these 3. In grassland soils, we see this deep, rich organic matter accumulation from the fibrous root systems. These are my favorite, by the way. We see this deep A horizon, which is soft and very easily molded and full of fibrous roots and pores and microorganisms, okay? Because of the grass roots. Essentially, that's what gives rise to this deep, soft, organic surface. In a deciduous forest, we see alpha solid development where there is rich surface horizons, but sometimes we see movement of bases, and maybe it's a little bit more acidic, and it's not quite as fibrous in its root system, right? Because it's mostly tree roots developing it. And so we see the additions of organic matter at the surface from leaf fall, but we don't see that deep, dark root system from fibrous roots that we see in grasslands. So it's a little bit different. Coniferous forests are pine needle friends. Now, pine needles are exceptionally acidic and they slow release acids over time, and generally coniferous forests happen where there's greater rainfall. So we end up seeing a lot more leaching and movement of things throughout the profiles here, and they're significantly more acidic. And in this example, we see a very, very leached out E horizon, all right? And we see lots of those leached out materials accumulating as iron oxides and humic materials in the subsurface. And this is a prime example of a spodosol. And we'll talk more about those later, but this is just a great example of the difference you will see in soil development based on the vegetation growing there. So much happening beneath your feet. Let's talk about factor 4, topography, where slope, elevation, and aspect make huge changes in how soil forms. Topography and parent material. Now, you will have to draw a landscape where you will identify the summit, the shoulder, the back slope, the toe slope, the floodplain, all right? So here at the surface, at the very top of the hill where it's flat, see it's flat up here, we have our summit. Right where the slope starts to break, just like your shoulder, we call that the shoulder. Where we have the steepest, longest portion of the slope, this is all the back slope. As we get to the bottom, the toe of the mountain, we have a toe slope. Out here where the water meets the start of the base of the hill, this flat area between the water and the base of the hill is the floodplain, all right? And we tend to see residual parent material at the summit, colluvial parent material where the back slope meets the toe slope, and alluvial material in the floodplain. Here's some examples of what you might see based on topography, parent material with different soil types. So here at the summit, this is what you may see versus the shoulder versus the back slope where it gets much deeper because water is able to move in different ways. Here in the foot slope, you're going to have deep accumulation of acute materials. Soil depth and topography is going to change, okay? So as you get into the lower portions of the topographic slope, you're going to see a lot more development of soil, as well as in the upland area, you're going to see more developed soil versus on the back slope where water moves too quickly for there to be extensive development, but especially true where you have shallow soils. The more shallow a soil, the sooner you get to bedrock, for example, the less development there is. The more depth you have to bedrock, especially if the slope isn't great, well, you're going to see a lot more development in soil profile horizons. And we'll talk more about that later. A catena or a topo sequence are soils with the same parent material. The primary difference is the topography. And the fifth factor, time, works in concert with other factors. It's a chronologically old soil, maybe developmentally young. Here we see arid soils, little development. Ideal conditions, hard to say. Okay. Time is one of those weird things where it matters, but it doesn't. You could see a soil that is hundreds of thousands of years older than another, but because of where it's located, maybe it's in a desert, it shows very little to no development versus a younger soil that's somewhere where there's a lot of rainfall and it's very hot is going to show much more development. So time is one of those weird factors that matters but doesn't. Does that make sense? If it doesn't, let's chat. So in review, I want you to know what are the 5 soil forming factors. Remember CLORPT, climate, organisms, relief, parent material, and time. What are the 3 types of parent material? Residual, organisms, and transported. Now remember, transported has 6 types of parent materials and what differentiates them. And finally, I want you to be able to define effective rainfall. Remember the soil's basic building process are additions, redistribution, and translocation, alluviation and illuviation, loss of materials from the profile such as leaching or erosion, and these all end up changing the soil. Horizons are layers of roughly parallel layers to the Earth's surface, and they differ from the properties above and below them. We've learned about the major soil horizons, but now we're going to learn about some of the smaller things that we will add on to these. So for example, we learned about organic surface layers, and we learned about A horizons and E horizons and B horizons and C horizons and R horizons, but now we're going to learn about the additional letters that we can add to this to indicate, for example, what is accumulating in the B subsurface horizon. Is it clay? Is it iron? There are subsurface designators that we add to this to help us understand. Now remember, this is a part of topsoil versus subsoil, but those subordinate horizon designations, that's what I want to focus on. We're actually going to have a lab where we go out to Cooper Farm and we start utilizing this information. So these are the lowercase letters, and the lowercase is important. We always add them onto our master horizon our master horizon. So for example, things that go with an A horizon are lowercase p's. In case it is cloud, we would write A. Hopefully this goes well. P. And the P is lowercase, all right? So there's an example of how we might designate a surface horizon that's been plowed. It would be an AP horizon. The little a and the little e is supposed to be an O, and the little I all go with O horizon. So we would have an OA horizon or an OE horizon or an OI horizon. D for densic, this is compacted till. This goes with C horizons. So we could have a capital C, lowercase d horizon. All right. G for gray or reduction. This can go with C or a B horizon, for example. So maybe we have a horizon that is waterlogged, and we would call it a BG horizon. Okay. The little r, this also goes with C. Okay, so capital C, little r would mean that you have a C horizon with very soft bedrock that you could dig through with a shovel. Slick and slides go with B horizons. So a BSS horizon is where we might have slick and slides. Please just let me draw a B. All right. The most common that you will see, this is supposed to be a B, folks. Work with me. All right. The most common thing that you will see in the subsurface in Indiana is a BT horizon. Oh, this is killing me. Used to having a whiteboard. This is rough. All right. Capital B, lowercase t, is where we have a subsurface horizon where we have clay accumulation. And we can have more than one of these, okay? You can also combine some of these horizons. We could have a capital B, hold on, this is going to be rough, stick with me. You can have a capital B horizon where we're accumulating something in the subsurface. And that thing that we're accumulating is clay, so we're going to put a lowercase t. But we also notice that that clay is really gray in color, so we're going to add a little g to indicate that it is gleyed. All right, so a BTG horizon, and it must be written in this order, the T always comes first, would be a horizon where we have clay accumulation and strong glaying. We could have a BTSS horizon, where we have a horizon of clay accumulation, where there are a lot of slickensides. Oh, please just let me. Okay, so we would write SS. A BTSS horizon would be a B horizon where there's an accumulation of clay and slickenslides. And I'll be showing you examples of what slickenslides are. I know you've probably never heard of that term. Stay tuned. Another example of a B horizon is a young profile where there's not much accumulation. So there's some horizon naming conventions. Example, BT. We use the uppercase B and then lowercase subordinate horizon designations to describe what's happening in the B horizon. Now, one thing you need to know about B horizons is that you will never, ever, ever describe a profile where a B horizon is naked, aka it does not have a subordinate horizon designation. Okay, B's must always be followed by a lowercase letter to describe what is accumulating in them, because by definition, they're accumulating something. So anytime you have a B horizon, you have to indicate in a lowercase letter what is accumulating there. And you can have multiple accumulations of clay. Let's say you have 3 horizons that are full of clay, but they each have different amounts of clay. Maybe the first BT horizon has 30% clay, and the second BT horizon is a different color and has 36% clay. And the third BT horizon is also a different color and has 45% clay. You see where I'm going with this? We would then call it BT1, BT2, and BT3 to differentiate them. Now, earlier when we were talking about parent materials, we were talking about different parent materials within the same horizon. So let's say at the surface, we have loess, which is covering residual parent material. In this case, because we have 2 parent materials, we would put a 2 in front of the horizon where the lowest parent material starts. We do not put a 1 in front of the other horizons where the loess is. We just put a 2 where the residual parent material starts. And we call this a lithologic discontinuity, meaning different parent materials. So here's an example profile where we have an O horizon, an A horizon, an E horizon, and then a whole bunch of BT horizons, 3 or 4, followed by a C horizon and then bedrock, known as an R horizon.